Here. You're already live?
Yep.
Oh, geez.
Figured I would go live. We're going to have to work on figuring out the exact lighting of this space. Because right now I have this giant cyclopean glowing eye right in my face, and that's probably not for the best. The reason why I started the chat early is, so this thing is going to be recorded and eventually posted to YouTube. I figured I'd give a little bit of a background. It's not really pertinent to the basics, but I figured I would actually discuss part of my interest in plate tectonics and why I think this is such a cool concept. When I was an undergrad, obviously I was born after the plate tectonics revolution, when the concept was sort of formalized by Harry Hess in 1960. But when I went to college, right around the end of the 20th century, it wasn't that it was a new concept, but it was still something that we were digesting. We were still investigating, and we still are to this day. But it was something that it just felt like it was still cutting edge, even though we're talking 38 years after Harry Hess had proposed his sort of omnibus concept, this sort of theory of plate tectonics. And it was something that just excited me because it felt like I could be part of that cutting edge. And it also felt like a very beautiful discussion where you could have an idea and then very discrete evidence to support that idea. I understand that biologists, they have the theory of evolution. I understand other disciplines have their own theories. But for me, as a student of geology, somebody who had loved geology, I mean, like most kids, I collected rocks and I put them in my pocket, et cetera, much to the chagrin of my parents. It was one of those things that I was just interested in because it felt like I could contribute, or I was part of this burgeoning science, or I was part of this new wave of thought. And the concept of that was particularly endearing to me and alluring to me, that I could then be part of this. Because if I study, for example, something like volcanoes, that's my specialty, I'm a volcanologist. If I study volcanoes, then that fits into the overarching theory. And it's not like I'm just studying some sort of like niche case out on the frontier somewhere. I'm studying volcanoes. And I think that that's kind of a cool concept. If I was studying earthquakes, again, it is part of the theory. It is one of the underpinnings of the theory. And so I think that's part of the reason why I was originally caught up in the concept of plate tectonics. The reason why I continue to be caught up in that is since I've become a college professor and I want to showcase how the scientific method works to our students. I can show, which we'll talk about here in just a moment, I can show Alfred Wegener and his ideas of how the continents moved, all of his observational evidence, all of his hypotheses, the test of those hypotheses, their rejection, and then the thought, well, okay, sure, we rejected all that, but where do we go from here? What's the next logical step? So when we actually have this as a concept, it allows me to showcase something that I know and I understand, and I'm not just sort of talking about it like third hand or fourth hand. It's something that I know and that I understand and that I've worked with, and I can showcase to the students all of the pieces of evidence, this sort of like bouncing ball, like a karaoke machine. I can show them all of the pieces of evidence that lead up to this grandiose theory. And then I can say, well, yes, this is really awesome, but we always have to realize that at the end of the day, it is just a theory. We could get new data and we have to throw it out or modify it and change it. And I think that is really cool. I think it shows a level of humility that we must have, the humility to say, we don't know. And if somebody comes along with something new, we go, okay, let's figure out what's going on. And the fact that we can use it as a predictive tool, for example, we know now, based on a whole bunch of the different studies we've done on earthquakes, volcanoes, et cetera, where we should focus our efforts in disaster preparedness and where we shouldn't, right? For example, we don't generally need to worry about earthquakes and volcanoes in Michigan. And if something should happen there, then we have to go, wait a minute, that just sort of completely bucks the entire system. But we could look back and we could go, oh, somewhere in the past, there used to be massive outpourings of lava in Michigan. And from the interaction with that and the water, we end up getting all the copper deposits. And that's cool. But we don't have to say today, you know what? The Michigan Emergency Operations Center really needs to think about volcano preparedness, because they don't. And if something does happen, then we really need to actually think about what that is. Okay, so it is 5 o'clock. I'm trying to get my cat out from destroying my laptop over there. This is the problem with filming in a house when you have cats. So I am Brett Burkett, co-owner of Blackland Geology and Reptiles. And one of our viewers, Max, had said, why don't you talk about plate tectonics? And I figured that was probably a fundamental good topic, because it showcases how scientific thought happens, how it has changed over the last 100 years. And it also shows how cool things have happened. Major changes in geology have happened in just the last century. So throughout the 17 and 1800s, we had sailed around many of the oceans of the world. And in sailing around the oceans of the world, we were able to map the coastlines of the continents. So we saw Australia, and we saw Africa, and we saw Asia. We saw North and South America. And as we mapped out their coastlines, and specifically as we refined over the next century and a half, as we refined our maps of those coastlines, we noticed an interesting pattern. For example, in this image here, we notice that Africa seems to spoon South America, and it sort of fits into the area between Florida and Maine. And when we had that, we went, the continents seem to fit together like puzzle pieces. Now, the human mind loves making patterns. So just because we have puzzle piece-like fit of the continents does not mean that at one time in the past, they were connected together. So scientists then went, well, is this just a lark? Is this just random coincidence? Or did they actually have connections in the past that we can find in the rocks, in the fossil record? To the latter part of the 19th century, geologists were able to collect data from looking at rocks, looking at fossils, and try and gather data from a whole bunch of different regions. And that in itself is a lesson where we could talk about sort of the growing science of geology and how we sort of rationalized we could use the modern experiments to look back into the past. But by about the turn of the 20th century, we had accumulated enough data that we might be able to now start making bigger generalizations and bigger connections. And that is amazing. Several people attempted to put all of this new information together in one place. But the person who really captivated the world with their collation of all this data and their discussion around it was Alfred Wegener. Alfred Wegener was a German meteorologist who made massive contributions to things like weather balloons and the way we measure atmospheric phenomenon. But he had this love for geology. And as the new data kept coming in, and as he went to professional conferences, as he read publications, he went, there seems to be something here that is more than just the general puzzle piece human mind likes patterns. So in the image on the left, what we're seeing are continents, and these sort of like Dalmatian-like spots there represent areas with rocks of unique chemical signature. So what does that mean? In the case of South America and extreme South Africa, we have this sort of pattern that if you were to study that unique rock in South Africa, you'd find it in South America. We'd find it in northern South America and Western Africa and sort of mid South America and around just south of the Congo, etc. We also found patterns where we could find unique rocks from North America to Greenland to Scandinavia and Western Europe. Alfred Wegener looked at those and he said, well, let's assume that that occurred by random coincidence. He said, what would be the probability that not only do you have the general overall pattern of the continents that look like they fit, but that the puzzle pieces themselves have demonstrable sort of patterns on them that link where you would expect them if the puzzle pieces fit? And he made one genius analogy. He said, imagine I give you a giant piece of newsprint, stories, pictures, it doesn't matter, and you cut it up into a series of rectangles and squares. Well, you could reassemble the initial outline of that rectangle and have complete and utter noise. These squares could be upside down, they could be backwards, and you couldn't read across them. That's random chance occurring without any sort of organization to it. And he said, you could do that. So I could give you a rectangle and you could rebuild the rectangle and it would be useless. And he said, but what would the likelihood be that you could recreate that rectangle, that sentences could be read across and you could actually get useful information from it? He said, the probability that you would get one line of information we'll call n, 2 lines of information n squared, and so on. And he said, we're dealing with multiple lines of information, so it is much more likely that they were connected than this all arose by random chance. He also specifically wanted to look at the fossils that were there, because if we have rocks, there can be processes in different places that can generate similar types of rocks. He said, but fossils are a little bit harder to actually rationalize unless you argue that they're connected. And the reason why is because fossils represent living creatures that had a range, a territory, they had patterns of migration, etc. So here on the screen are 4 distinct fossils. 2 of them are land reptiles. The one in the lowest corner, Mesosaurus, is a freshwater swimming reptile. And then we have a fern. And he said, okay, let's look at the land reptiles. How does a land reptile get from Central South America to Central Africa? How does a land reptile get from Central Africa to Madagascar to India to Antarctica? When he presented that as an idea, some scientists said, land bridges, everybody knows, and never start a sentence. Never start a sentence with everybody knows, because it's immediately false. Unless you are the only person left alive, you're going to find somebody that doesn't know something. He said, people argued everybody knows that the peoples that came into America came across land bridges from, say, Western or Eastern Siberia. So if they came across these land bridges, then it stands to reason that we could just have bigger land bridges that connected the continents. And he said, the estimates for those land bridges across from Siberia to Alaska was about 60 miles. Now you're talking 3,000 to 6,000 miles. And they said, well, prove the land bridges don't exist. And he said, well, I can't. Why? We hadn't really studied the floor of the oceans, so there's no way to prove that the land bridges don't exist outside of more common sense. But he said, this is a freshwater reptile here. In between, there's 6,000, 7,000 miles of salt water. So unless you're arguing that that land bridge is 7,000 miles long and has a freshwater trough in it that would make Michael Phelps jealous, he said, that seems to be ridiculous. And he said, the other problem with that logic is this. If you have these land bridges, then could you imagine how many predators would just cluster along the edges of the land bridges? Because if they were forced to migrate across there for breeding, food, or whatever, that would be a narrow opening and they would just like waiting maws collecting all of the animals. So he said that doesn't make any sense, but he couldn't prove that he was correct. The fern is my favorite one because if we argue that a plant broadcasts its seeds, it's probably not going to follow a narrow band that just connects one section of South America, one section of Africa, Madagascar, southern India, Antarctica, and a weird Nike swoosh, and Australia. That doesn't seem to make any sense. That can't be argued to be land bridges unless we're talking Pokemon. And it's sort of a grass mobile creature that moves across the landscape. So Alfred Wegener wrote a book called On the Origins of Continents and Oceans in the latter part of the 1910s. And when he published his book, you could tell that he had gathered an incredible amount of data to sort of silence critics. The problem comes in, everybody wants to know one question: how? How can the continents move? You have a lot of evidence that suggests that they have. How can they move? And it was fundamentally evident from reading his book, he was loath to actually make up a mechanism, because gathering evidence, people would go, well, that's good evidence. But if you gather all of that evidence, then you next have to say, how does all of that fit together? And he was loath to do that, but he did. And his argument was this: the tides, the pulling of the moon on the earth, will actually influence the oceans. We know this. If you go to Houston, the actual sea level will rise and fall as the earth rotates on its axis, and portions of it come in range of a direct line to the moon and then move away from that. On the next image that you'll see here, what we have is a high tide and a low tide, sort of the orientation of the moon relative to the sun, relative to the earth. And the pulling of the moon on the oceans can create rises, raises, and lowering. Sure. He said that same logic could be applied to the continents. The oceans move very quickly. The continents are just pulled very slowly. But we run into two problems. One, the force is much too weak. Second, there's a logic problem. If the moon is able to pull the continents, but the earth rotates once every 24 hours, then a continent is tugged toward the moon, but very quickly it now moves to the other side of the planet, so it would be tugged back the other direction. So there should be no net movement of the continents. The only way that there could be net movement of the continents is this: if the continents moved once every day around the globe, and they just sort of like a tug to sort of drag them, and we know that doesn't happen, because otherwise that would be like on the California side, massive waves like a jet ski, and on the other side sort of slack water with a wake behind it. And we don't have that. We don't have this giant Australian wake. The other problem he ran into is this: if all of the continents were joined together at some point in the past, we only have one moon, so why would they separate? So if anything, they'd be gathered around the equator and then just sort of orbit the Earth or slide around the Earth at the equator. So it didn't work. When he presented his ideas, scientists in Europe went, okay, you have a major problem with your mechanism to move everything, but they didn't discount his evidence because it was damn good evidence. In America, most of the scientists got behind Wegener and they said, we need you to come up with a better mechanism. But two famous old American geologists said, nonsense, can't happen. Everybody knows the continents don't move. It has to be land bridges. But where are these land bridges? I don't know, but they have to be there. And the process got somewhat stymied because we didn't have evidence for the land bridges in the ocean, but we didn't have evidence against them either. Now, you would think that that could be the end of the story. And for Alfred Wegener, it actually was in the late 1930s, trying to find more evidence to prove his idea, what he called the continental drift hypothesis. He ended up losing his way in Greenland and freezing to death. But being that he had gathered so much evidence, then we then had to go, well, what do we do with it? Something is going on. The thing that helped us was actually a parallel discovery that had been made in the late 1800s and then into the 1900s. And that parallel discovery was earthquakes. In the late 1800s, I simplify, of course, but this very simple circle, core, and mantle, we knew that the Earth had to be layered because we'd made gravity measurements, we'd estimated its mass, we'd estimated the density of the planet, and all of the rocks that we could see, they didn't jive with that density. So it suggested if we have some really high average density, but all we're finding is light rocks, there has to be something denser. So by the late 1880s, we had this. There's sort of a light rock covering a solid interior. Today, we have this much more complex, exhaustive diagram that we have on the right. And the way that we are able to go from one to the other in just the last, actually, from 1880 to about 1930, in the 50-year time span following this sort of simplistic model that we have on the left, was due to earthquakes. We had created a device to measure earthquakes in the latter part of the 19th century, and then we improved on that and tried to do more measurements to figure out what that actually meant in the early part of the 20th century. So how did we do that? The deepest we've ever dug in Earth is 7.2 miles. And the 7.2 mile discovery was actually made in Siberia. It's called the Kola Super Deep Borehole. And they drilled a 10-inch hole 7.2 miles down, but they ran into trouble. No matter what they could do, they couldn't actually drill any farther. And we have never beaten that depth measurement because it's just too hot as we go down, and they couldn't get enough drilling mud to keep the bits lubricated and cool. So the bits started to melt. If we cannot dig into the earth, how do we figure out the interior? Well, we figure it out in a similar way to doing a CAT scan or an MRI. With the human body, we don't want to open it up at all times. We don't want to, oh, there's something on the brain. Okay, let's open it up and find out what it is. So what we do is we have created remote viewing technology. I guess technically remote sensing. Remote viewing is its own animal. We created remote sensing technology to be able to look into the human body, and based on work with cadavers, we were able to understand what was going on inside the body. For example, a picture in the upper left-hand or right-hand corner, blood on the brain. Why? Because the data that we are sending, the particular energy that we are sending through the brain, is interfered with based on the density of the materials. So liquid shows up different from the sort of more solid, squishy material of the brain. There's a good biological word there, squishy. With the Earth, we did something similar. We had a device, a seismograph, which we'll discuss here in a minute, that was able to record earthquakes. And then we were able to do experiments in a lab trying to generate those earthquakes, sort of like we would experiment with cadavers to try and understand what was going on. So the earthquakes that we have, earthquakes are no different than a sound wave in the earth. They still have a wavelength, they still have a frequency, they still have an amplitude. They are no different than other types of waves. The only difference is their mode of transmission. Right? So light waves has its own frequency, wavelength, etc. Its mode of transmission. Sound waves are the same thing. And even the word seismograph or seism or seismology is the study of sound or study of ground motion, right? But it's really sound. When we talk about an earthquake, we are actually talking about 4 distinct wave types, 4 distinct signatures that all interact and overlap with each other. What does that mean? Every earthquake generates 4 distinct wave types. They're all generated at the same moment, but they move in different ways, and they can be broadly grouped into 2 categories. Body waves, waves that pass through the earth, and that's what we're going to focus on, because if we're trying to talk about what's going on in the earth, we want to know stuff that goes through the earth. We don't care about stuff that goes on the surface. And then surface waves, waves that affect the earth's surface. So one earthquake generates 4 types of waves, and we're going to focus on 2 of those, what we call the body waves. There are 2 types of body waves. And if you know anything about geology at all, or anything about, you've read anything about earthquakes at all, the 2 types we call the P wave and the S wave. A P wave is a wave of pressure. It is the first wave that people experience in an earthquake, whether they perceive it or not, because it is the fastest type of wave. And it's usually the sudden jolt that people experience when they suddenly go, is that an earthquake? And that's what causes people to freak out. My first experience with an earthquake, technically I've been through several, but the only one that I actually perceived, because I'm a generally insensitive person, was one when I was in remote Peru, and I'm sitting in a small bed. It's the end of the night. I'm really tired. I have my water bottle on sort of a bedpost, and suddenly the bed just starts slamming against the wall. And I look over, and my field assistant is there, and we both just sort of freak out because we realize we have learned this for years, but this is the first one that we've experienced. And I run downstairs, and I'm like, earthquake, earthquake. And they go, it's just a tremor, go back to sleep. But what I had experienced was the P wave, and that's what caused everything to rattle. It is a wave of pressure. As you can see from this animatic here, and it is working, the animatic is working, good. You can see that it's a wave of pressure, much like if I took a slinky and I hit it on one end, then I'd see a wave that sort of propagates through it and everything squeezes and then stretches back out. If you look at the black square does move forward, then it moves back, and it stretches and compresses, but it doesn't have any long-term movement. That wave of pressure can move through a solid, a liquid, or a gas, because I can squeeze a solid, I can squeeze a liquid, although not easily, and I can easily squeeze a gas. The neat thing about that is this logic. That means that a plane could be interrupted in flight by an earthquake because the P wave travels through the atmosphere. That is the fastest wave type, and it travels in the crust at about 7 to 8 kilometers a second, which is about 4 to 5 miles per second, which means if an earthquake occurred within 15 miles of you, like the average sort of car drive, that would be 3 seconds and you'd be affected by it. The second wave that we experience is called, conveniently enough, the S wave, or the secondary wave. And it is a slower wave, about 60% as fast as the P wave, so about 3 to 4 miles a second. It is a wave of shear, and the easiest way to visualize this is if you grabbed a bed sheet and you were trying to, as we always called it growing up, fluff the bed sheet. You grabbed it at one end and you lifted, and then you pulled down dramatically, and you created this roll that propagates along the bed sheet. That would be the S wave, and they work perpendicular to the P wave. It can only move through solids. And the reason why is because if I have a solid where atoms are connected to each other by defined bonds, if I lift on one, the other one must respond. In a liquid, the bonds are only temporary. So if I lift on one, the rest doesn't care. And in a gas, there essentially aren't bonds between the molecules because they're zipping in different directions. So if I lift one, the rest of them don't even know that I've lifted it. And we know that because if we've ever been in a pool and you see the kid and the kid is chopping water with their hands, when they lift one hand, there's not a tube of water between their hands like a water bender. Just doesn't happen that way. Wish it did, but it doesn't happen that way. So what do we care about with those? We can make this statement. Through experimentation, we've learned that both P and S waves travel faster through denser and more rigid material. And for our purposes, this is the most important thing. Why? What we've been able to then do is this, knowing that the P wave travels through solids, liquids, and gases, and the S wave only travels through solids, and that they are both generated at the beginning, that means that if I am listening for them and I hear a P wave and not an S wave, I had to have hit a liquid or a gaseous body. This is how we actually look for oil. We bring in a device that thumps the ground, and as it thumps the ground, we can sort of listen for an echo. And if we hear an echo of a P wave and not the S wave, we go, we've hit something. If they travel denser through more rigid material, and the key word there is and, how does that make sense? Well, if the atoms are closer together, any motion between the atoms is going to be more strongly felt if the atoms are closer together. So through experimentation, we found that both P waves and S waves travel through denser and more rigid material. Why more rigid? Because if everything is just sort of moving about, then probability, you're not going to have everything nicely next to the thing that it needs to hit into, for example. I tell my students, this is like a bucket brigade. The classic picture we have of the bucket brigade, everybody in a line, somebody pulls the bucket up from the well with water, they pass it down the line, it moves to everybody else. Well, if you have one person that's just not paying attention and they're just sort of moving around and looking about, that's not efficient to transfer energy. But if everybody's nicely positioned and they're close together, that way you don't have to chuck the bucket to anybody, waste time moving. So why does that matter? If we look in the earth based on innumerable experiments, we have an earthquake and we listen and then we try and understand what just happened. What we found out is this. The deeper down we go, the denser it is. And in general, the deeper down we go, the faster the waves travel. An incredibly busy diagram just appeared on your screen. And when we see this, we'll see two things, depth toward the center, and then at the top, velocity, how fast everything's moving. We have a red line for the P wave, and the P wave is, in all cases, faster than the S wave. We see the S wave stop in the earth. There is a portion that if we're listening, depending on how far away we are from the actual motion, the initial, what we call the focus, where the ground breaks in the first place, and we listen and we don't hear anything. There is no S wave, and the P wave slows down dramatically. Why? That's what we think the outer core is. The outer core, we imagine, is liquid. Experiment says it can't be a gas. And because the S waves stop, it can't be a solid. The P waves slow down because it's not rigid. It's a liquid that's sort of moving about, because that's the best gesticulation, I guess, for a liquid. If we have this, what do we see? S wave stops, we don't see it again. P wave slows down dramatically, increases to the bottom, then we get a speed jump, and we get then what we think to be the inner core, which is solid. So what do we have on Earth? We have a crust, and we'll talk about it. It isn't shown here, but it is basically the top line because the crust is so thin. The greenish thing is all the mantle, blue outer core, the light blue, sky blue inner core. If you look at those two top layers though, and this seems like it's getting into nitty gritty detail, and I promise you we're gonna see how all of this connects. If you look at the top piece, we have the lithosphere, lithos, rock, sphere or shell. So we have the rock shell, and the asthenosphere, it is a weak layer. And geologists went, what do we call the weak layer? Well, what's the word for weak? Astheno. Okay, so we're gonna call it asthenosphere, which means weak layer or weak shell. Why? How do we know? Well, you can see on the image on the left, there is a slowdown, a subtle slowdown in the asthenosphere, and I've greatly enlarged that on the image on the right. So if we look at this, the asthenosphere is where we call that low velocity zone. Who cares? That layer suggests that it is weak, but is still solid. So it's more like silly putty or Play-Doh, something that is deformable, to use my gesticulations, deformable. And we think that is now the reason that the continents can move around the globe. How is that even possible? Well, the lithosphere, the rock shell, sits on top of a weak layer which acts as a lubricant. So if you hear the term plate tectonics, and we have this idea of plates, what are the plates? Chunks of the lithosphere broken up like an eggshell, moving on top of a deformable material under it, which is our weak layer. How fast does it deform? Slowly, but on the orders of, say, thousands of years. I'll give you one by the very end. If we have time, I'll go and I'll give you one example, which is more recent. We went, uh-oh, we never thought about that. So how does this all matter? As we also got more and more refined measurements, we realized that even the crust of the earth, the top surface of the earth, was made out of different things. The floor of the ocean was made out of an iron-rich material. The floor of the continents was made out of an iron-poor material, granite, largely. So on this image, I want to show you two things. We have a very thin ocean crust and a much thicker continental crust. Then we have this thing below it that's sort of given in like a brown mottled color. The crust, whether it be ocean or continental, and the top part of the mantle, we call the lithosphere. That's our rock layer. And then the bottom, which is unlabeled, it's just all lumped into upper mantle. At the scale of this image, that would be our asthenosphere. So the crust and the top part of the mantle moves as a unit, our little candy coating or eggshell moving on the lubricant below. We actually had a pretty good idea of the existence of the asthenosphere by the early 1920s. And this is amazing because by this point in history, we had gone from creating a seismograph that could record earthquakes in the latter part of the 19th century, the 1800s, to being able to figure out the layering, the overall structure of the earth. And even if we didn't have the exact depth down, we had a pretty good idea of position. And we had discovered by, I think, 1923, the existence of the asthenosphere. I have a book from there where they're actually digesting what it is. By the latter part of the 1930s, a scientist named Arthur Holmes came up with this idea. He said, what if that asthenosphere acted as a lubricant for the stuff above? He said the ocean crust would separate. Now, we'd argue today the ocean lithosphere would separate along these big ridges that we were starting to see in the middle of the ocean. Hot magma would come out of them, and as they would come up, eruptions would occur on the ocean floor. We'd get cooling, we'd get formation of new ground, and then we would get sinking along the edges, much like a convecting pot of soup. And he said, why would this all be driven? Well, logic. The hotter down you, or the deeper down you go, the hotter it is. And he said, this would make some sense. Now, This was a hypothesis that we needed to find evidence for. But think about this. Not only did it happen rapidly after the discovery of earthquakes and the fact that we knew what earthquakes were, but the fact that we could actually measure them, record them, and discuss, but that we could then put that together by 1928, and the fact that this is only 92 years later, and we look at it like, oh, that was formed so long ago. 92 years is not that long ago. The mantle from its top to its bottom is solid, but there are parts of it that are weaker than others. And what you're going to see pop up here in a moment is a diagram explaining how we think the mantle actually behaves. The lithosphere sits on top of the asthenosphere. The asthenosphere is hot, it is deformable, and it moves like silly putty. It is very close to its melting temperature, and that's the reason why it's so deformable. If you've ever tried to do something like heat up honey, we know that when honey is cold, it's basically Vaseline. When we heat it up, it starts to decrease its viscosity and flow much more easily. In the case of the asthenosphere, it is very close to its melting point. It wants to melt because it's so hot, but pressure keeps it compacted so that it can't expand. Why is that important? Unlike water, nearly every other substance that exists on Earth, the liquid form is more expanded than the solid form. It needs space to grow. Well, the pressure of the lithosphere actually sits on top and keeps it from melting. But if you look down these three diagrams here, if Holmes was correct and the lithosphere was stretching, it would stretch and get thinner and the pressure would decrease, and that could allow it to melt. It's like our idea of a jack in the box. We turn the handle, the spring keeps on building up pressure and pressure, and in that case, it is pressure which overcomes the lid, pops it open, and out comes that nightmarish horror that we had when we were children. In this case, now temperature is pushing up, essentially. Temperature, it says, I want to expand, give me room to expand. No, now it stretches like taffy, and now I have that room to expand. The mantle is hot, it's solid, but it's under high pressure. The crust splits, temperature wins, and now we get melting. So who cares? At the same time that all that was going on, World War I happened. And then eventually World War II. And the new introduction into warfare, planes, submarines. For our purpose, submarines. In order for us to propagate submarine warfare, we needed to know where the Nazis were hiding their subs. And conversely, they needed to know where we were hiding ours. That forced us to then scan the ocean floor and make maps of the ocean floor, which we hadn't previously done in any great detail. What we ended up finding is in the middle of the Atlantic, there was a massive ridge system. And that massive ridge system, you're going to see an image pop up here in a moment with black dots on it. The black dots represent the epicenters of earthquakes that we were able to map out over a 15-year period. And what we found, not only do we have a really weird ridge in the middle of the Atlantic, but that ridge is what we would call seismically active. There are earthquakes occurring along the top of it. We also have a similar ridge system in nearly every other ocean basin. And what you're going to see pop up here on the screen here in a moment is a picture of earthquakes for about a 50-year period on Earth. And we can see that they are not random. There is some organization to them. And these earthquakes seem to appear in discrete bands that look like the edges of puzzle pieces. These discoveries were made up through about 1940, so that we had some really good pictures of not only the coastlines, not only the rocks, not only the fossils. Wegener did that 30 years prior, and so did his predecessors, but the earthquakes, where they occur. And when you look at this, they are not random. We do not, for example, have earthquakes in Wisconsin. Right? On this, we don't see earthquakes in Wisconsin. We don't see earthquakes in Alberta, Canada. We don't see earthquakes in most of Greenland. In Western Africa, we don't see earthquakes. Give me 1 second. Okay, so this is the danger when you're looking to see if somebody's commented in the chat and then you get a phone call.
I'm looking.
I know, I just got a phone call. So Now, if you look at this image, you actually have two distinct things. You have sort of these thin bands, which I've identified for you as mid-ocean ridges with a series of dots on it. When you have those series of dots, those are mid-ocean ridges, but there seem to be areas where you have many, many, many more dots. For example, west coast of South America, west coast of Mexico, western United States, Alaska, Japan, eastern Australia, Indonesia, etc. We're going to come back to those. But if you look at the earthquakes, we have these mid-ocean ridges. So now that got us thinking, maybe Arthur Holmes was right. Maybe those represent areas where the crust is splitting. And then we went, well, a little bit of logic. If Arthur Holmes is right, and the crust is splitting there, what we now say the lithosphere is splitting, because it's more than just the crust. If the lithosphere is splitting there and new ground is being created, shouldn't we be able to find that out? So what we did is we sent out ships and we drilled into the floor of the ocean. And then we figured if new material was being created along the mid-ocean ridges, well, it should be younger than the stuff that's farther away from it. And when we sampled it, and that took us a lot of years because that's not easy, and we did all of the radioactive age dating for it, what did we find out? Yes, it was correct that the stuff closest to the ridges was younger than the stuff that was farther away. So one of the challenges, though, was this. Let's assume that Arthur Holmes was correct. And if we assume that he is correct, then doesn't that mean the crust constantly grows? And if the crust constantly grows, why doesn't the Earth grow in size and decrease in density? Well, it isn't that the Earth continues to grow. There has to be some recycling. We create one place, we have to get the material from somewhere else. So what we think is going on, I've shown you here now on the left-hand side of your screen, volcanoes of Earth. And where most of the volcanoes tend to occur is in the areas with those incredibly wide bands of earthquakes. For example, western coast of South America. What we think is happening is that the lithosphere, the ocean lithosphere, is sliding under western South America, and that creates several things. The collision between those creates mountains. The fact that one piece is sliding under another and going into the hotter mantle creates melting, which gives rise to volcanoes at the surface. And we get this incredibly deep valley on the western edge of South America. Why? Simple geometry. If I have a plate that's like this, and then something breaks and moves down underneath it like so, you'll eventually see that there is a V that should form along the edge. Along the areas where we have those dense bands of earthquakes, we have ocean trenches. And the oldest material compared to the mid-ocean ridges are there. And so what we're doing is we're creating new material, and we're recycling the old material, and that's amazing. Now, what I'm going to do over the next couple slides is show you examples and talk about the exact specific processes that go on there. If you have questions, throw them in the comments because I want to know and I want to be able to address those. You'll hear it said something like this. There are 6 major plates and 11 minor plates. It doesn't matter. The Earth's surface is broken up into plates, and those plates are from the lithosphere. The lithosphere itself is broken up into plates. Some of those plates represent areas where collisions occur, and we can see them on here called convergent margins. That's where collision is occurring. The mid-ocean ridges represent areas where the lithosphere is splitting. We call those divergent margins. And it even makes sense. Divergent, divorce, separation, convergent with coming together. There is a third type, which we will talk about, but it's not drawn on here because it's hard to show on an image like this. But if you look, you can see areas where we expect lots of collisions, for example, Japan and Indonesia, and areas where we expect lots of separations in the middle of the Atlantic. It really doesn't matter how many big plates or how many small plates there are, because that's like the argument where we get into and we go, well, there's 7 continents. Why are there 7 continents? Why is Greenland a continent, or not a continent, and Australia is? And if you say, well, it's plates, we didn't know that when we came up with the concept of continents. And if that's the case, why is Europe and Asia, why are they separate continents? And we go, mountains. Okay, but lots of places have mountains, right? Why don't we just call it all like Afro-Eurasia, right? And America. But for some, that is a conversation for another time. If we look at the earthquakes of the world, an image is going to pop up here on the screen with the earthquakes. Back here, we have our mid-ocean ridges, and we have our question areas. The areas with the denser bands of earthquakes, so sort of wider bands, are the areas that are associated with most of the volcanic activity on Earth, most of the earthquake activity on Earth, most of the tsunami activity on Earth, because earthquakes under the ocean tend to displace water, which can create tsunami. The biggest earthquakes in Earth history have occurred along these areas, because we are talking about taking a huge section of the Earth, the lithosphere, and rubbing it, grinding it against another huge section as it descends below. So we get major earthquakes here. The largest earthquake in Earth history occurred on the Chilean border, right? The Chilean coastline. In 1960, we had a magnitude 9.5 earthquake. Surprisingly, it killed actually very few people because it occurred early in the morning. Most people were at home and they lived in the mountains, so any tsunami didn't really affect them. We still had about 3,500 deaths, but given the fact that that was the largest earthquake ever recorded, that is impressive. Those bands of dense earthquakes and the volcanoes they produce, you've probably heard it called the Ring of Fire, right? To go back and hearken to Johnny Cash. The reason why we call it that is because they tend to, the largest collection of earthquakes and volcanoes seems to form a disjointed but somewhat general ring-shaped feature in the Pacific Ocean, and that's what we call the Ring of Fire. You can see on here, in the last 50 years, this image is kind of old, so there have been new ones, but basically the same idea. We can see the stars, and then we can see areas where we have these deep valleys. So what's going on? Let's look at some of the interactions between the plates. I'm going to talk about the general science behind them and then show you some specific examples. On the screen here in a moment is going to come up our image of a divergent plate. So plate separation. Divergent plates, by and large, happen under the oceans, but they can happen in continents. And I can spend an entire lecture talking about divergent plates in continents. But our general idea from this really simple animated GIF is separation and magma comes out. You can see it shown as lithosphere with the crust above, which is part of the lithosphere. The asthenosphere is what is melting. If we do that, do we get major volcanic eruptions? No, because the lava comes out with a very low viscosity, and I put this in the other lecture that I did on volcanoes, and it cools under the ocean, and so we don't generally get any major eruptions. We also generally don't get any major earthquakes there. The biggest earthquakes are about a magnitude 5, which is respectful, but nothing severe. We don't really see, I'm going to come back to this image. I moved away from it. You'll see it flick for a moment. We don't really see any major volcanoes that crest above the surface on divergent plate margins because the nature of separation and them being underwater, we don't really actually see it. The only time that we really see it is in Iceland. Iceland is a very strange setup where Iceland is a strange volcano that is on top of the mid-ocean ridge, and specifically the mid-Atlantic ridge. And so you get this weird, stretchy island, which is characterized by volcanic activity and a whole bunch of linear fissures on it as the island is physically torn apart. But we don't really see any of the classic volcanic, like giant conical things or whatever. We don't see that on mid-ocean ridges, right? Let's talk about convergent. Convergent can happen in 3 different ways. The edge of an ocean plate, characterized by that thin ocean lithosphere, strikes another ocean plate. An ocean plate strikes a continental plate, or 2 continental edges meet each other. The easiest case to talk about is when ocean plates actually meet. An image is going to pop up here on the screen in just a few seconds, looking at Japan. And the reason why I like this particular one is we can actually see it on Google Earth. In the upper left-hand corner, Google Earth, the red triangles represent volcanoes, dormant and historically active. Shannon.
Yes. What?
Cat.
Yeah, she's just over there. She's not.
Okay. On the lower right, it shows what we're actually sort of a schematic of what we're seeing in the upper left-hand corner.
She likes the colors.
I know. She likes the colors of our new computer. I just don't want hair in it. So what do we get here? Japan is what we call an island arc. And the reason why we call it an island arc is very simple, because as one plate slides under another one and creates this sort of new melting as it moves into the asthenosphere, the liquid comes up and it tends to form a sort of deformed, general curved structure, which we call an island arc. Japan is at a very interesting juncture because it is the interesting juncture of three separate plates: Pacific Plate, Philippine Plate, and the Eurasian Plate. And the flat area that is next to Tokyo, what we call the Yokohama Plain, one of the most fertile, wide areas, flattish areas in Japan, occurs right at the juncture of those three. And Japan itself has been bent in this weird angle as a result of plate activity and the different interactions from the north end to the south end. The nature of the volcanoes are slightly different. The depth of the trenches off the shore are subtly different. And the earthquake potential for Japan is subtly different from top to bottom. The most recent 2011 major earthquake, which is a magnitude 9 earthquake that generated the tsunami that, of course, killed lots of people and hit the nuclear power plant, actually happened on the northern section of the Pacific Plate versus the Eurasian Plate. And if anybody's interested, I will give a lecture on the Japanese, what they call the Tohoku earthquake and tsunami. I would love to do that. This is what we tend to see in those scenarios. This is what we would call ocean-ocean convergence, one ocean plate sliding beneath another ocean plate. And the volcanoes we tend to see there are explosive. You can get effusive ones, sort of the more runny lava, but they tend to be on the more explosive end. And what we tend to find is this. In those scenarios, we can get tsunami. Why? Earthquakes generate tsunami. Volcanic eruptions can throw products into the ocean nearby and generate tsunami. For example, pyroclastic flows into the Sea of Japan on the west side of Japan have been known to cause tsunami because they're still displacing water. The earthquakes can reach terrifying magnitudes. For example, in the case of Japan, they had a magnitude 9.0 earthquake. In Alaska, in 1964, we had a 9.2 or 9.3 earthquake. In the same general idea near Anchorage, we had also this kind of interaction. If the plate is an ocean going under a continent, now something else changes. The continent is, especially in the crust, is made out of largely granite, and that has a low iron and magnesium content. When it melts, it tends to be more viscous, more explosive. So let's look at South America. In the case of South America, you have an ocean floor sliding under South America. And when the volcanoes are generated, they are not generated iron rich, they are generated intermediate to low iron concentration, making them remarkably explosive. And I see a note from Max here. It's kind of
Yeah, I got it.
Yes, absolutely. And that has to do a little bit with the nature of how the plate itself may actually not be nice and uniform. So the visual that we have of one plate sliding under another isn't just a one shelf sliding under another. The edge of the plate itself can be warped, and that can change locally the nature of earthquakes. If you look, and we'll go back to it for just a moment. If you look at South America, South America has really 4, but you can easily see 3 distinct bands of volcanoes on it. And you can see how this could apply to Japan. The image will pop up here in a moment. The 3 distinct bands of volcanoes in South America come as a result of the plate itself being warped. So if anything, the plate itself, as it slides under South America, looks like more the edge of a seashell, like a clamshell, where we have these sort of irregular folds in the clamshell. And so in areas where the clamshell is somewhat horizontal, so the plate is sliding under at a horizontal angle, we tend to not get volcanic activity because the plate doesn't descend deep enough to actually give us any significant melting. When the plate is coming in steeper, so imagine that idea of the sort of rippled shell and we get the tilted edges, then it comes in steeper and we get volcanoes. So we end up getting 3, and if you would be able to zoom in there, really 4 distinct bands of volcanoes in South America. I would imagine that Japan is similar. Maybe not as convoluted, but I would imagine it's probably similar. This is another reason why I really like plate tectonics, because it isn't nice and uniform. We have a general overarching idea, but then the nuance, the devil's in the details. When we look at South America, there we get much more explosive volcanic activity, and it moves into the remarkably low iron and magnesium end. And so we get eruptions that look like our nuclear bombs. You'll see three pictures here. The one in the lower right is El Reventador in Ecuador. The one in the upper right is Sabancaya, I think, and I forget which one. The one in the lower left. I just have pictures of volcanoes. I'm like, they're cool, and I slap them up here, and then I have so many pictures that it's like family pictures. Okay, I don't remember when that was. But if you notice, in all cases, there's sort of an intermediate to a light gray color, and then depending on the nature of what time of day, you can get these beautifully weird and ominous sunsets. In this scenario, we can get really explosive volcanic eruptions that generate pyroclastic flows. We can get earthquakes that manifest in the 9 to 9.5 range, because Chile was like this, right? Giant chunk of ocean floor going under South America. And we can, of course, get tsunami, but being that we're dealing with stuff that is under a continent, the tsunami tends to affect the edges, and then that tsunami can propagate away out into the Pacific Ocean. That doesn't necessarily protect them, but in the steeper mountains of the Western South America, Chile was largely protected from the tsunami, but the tsunami that was generated in 1960 hit Hilo, Hawaii, which is amazing to think that it can actually travel that far. If we get two continents merging, this is how we think the Himalayas were formed. And an image is going to pop up here on the screen with the most egregious pastel schematic, and trying to showcase how we think India moved. And given that the GIF was made a while ago, you can tell that we just didn't have such technical detail for fixing, doing image processing, etc. So it just looks like, oh, this red blob sort of squeezes in. But what we think is that Southeast Asia, Vietnam, Laos, Thailand, Indonesia, was deformed out of the way as India moved northward and collided with Asia about 75 million years ago. It started moving north. We actually have fossils in it. The fossils nearest the surface suggest that they were formed in a southerly latitude south of the equator, and then over the last 75 million years, they crossed the equator. We can see in the fossil record that we can see them cross the equator. And then about 25 to 30 million years ago, the outer edge of India started colliding with Asia, and the Himalayas were built upward. The Himalayas are the tallest mountains above sea level, and they generally do not, although you'd think they should, they generally do not decrease in volume or in height. And the reason why is because even though erosion is breaking them down, ice is weathering them apart, India is still moving northward. And so it is a slow motion car crash, which is keeping the Himalayas roughly at their same height throughout time. So we actually call this the sort of joke is that this is mushy tectonics. So tectonics, the action of moving bodies, etc. So in this case, this is sort of mushy because the visual that we have, imagine you had a block of wax and you punched it, it would flex around your fist. And that's roughly what Asia did around India. So that covers the three different ways that plates can interact when they are colliding with each other. Now let's talk about the two other cases and then a funny story. The two other cases, and I understand this can get complex, but obviously I've spent so much time studying, my students will look at this if they do and say, you do realize that you took 4 days in lecture to cover what you just did there in an hour. And I went, yeah, because there's always more. If we look at this, southwestern United States, we have a very interesting setup because in the southern area, which is actually in Mexico, we have separation, divergence. We actually have a mid-ocean ridge in what we call the Gulf of California. This is this little tiny blob of water between the Baja Peninsula and Mexico. we actually have separation occurring here. And on the northwest coast, off the northwest coast of North America, we have separation occurring here. So another mid-ocean ridge. The line that is in between them, we call the San Andreas Fault. And it is like a zipper. The zipper is opening at the bottom, and the rest of the San Andreas Fault is feeling the effects of that and is being torqued, T-O-R, with this being torqued. And it is like, if you imagine opening a zipper, the rest of the fabric flexes as the zipper moves up, right? The southwestern coast of North America, including the Baja Peninsula, is moving up the coast relative to the rest of North America. This is the essence of the idea that you have probably heard. What, is part of California going to fall off into the ocean? No. So many people have asked me that question. I think that they hope that it will happen. But the idea that we have here is, as the Gulf of California effectively gets longer and as opening happens in that last little bit of Mexico below the US border, the rest of the west of southwestern California is going to slide up the coast. The reason why it's called the San Andreas Fault is in 1906, we had a massive earthquake, wiped out San Francisco, 250,000 homeless, 3,000 dead. And the governor of California said, never again, we have to figure out why this is happening. So geologists went from the Gulf of California to San Francisco, and they found evidence in the landscape to suggest that southwestern California was sliding up the coast. They called it a fault because fault is the idea of error. The earth has an error with it. And the end of that fault disappeared under Lago San Andreas. So they called it San Andreas Fault for San Andreas Lake. The thing which I think has prejudiced people to think that California is going to fall off into the ocean is the first Superman movie with Christopher Reeve. Because Lex Luthor's master plan was to detonate nuclear weapons on the San Andreas Fault, break California, southwestern California, off from the rest, and he had bought up the desert so we could turn it into beachfront property. Think about that. And the entire, at the very end, Superman has to fly under the San Andreas Fault and lift continental chunks back up and stick them back on. But the visual that California, and he has this elaborate glass floor to show what he's doing, and then he takes his cane and he stabs it in, and southwestern California breaks off. And people went, California is going to break off. I think the other thing happened because if you imagine me trying to explain this, or any scientist trying to explain this to, say, a reporter, they would go, hey, okay, here's the science. And then we went, well, how do I turn that into something? And then because there's this sort of slight disconnect coupled with that movie, then people went, oh, okay, that's what happens. At best, west of San Francisco might become a peninsula. We do not know the full story because on the West Coast, in Northern California, Washington, and Oregon, what is labeled there as subduction zone is a chunk of ocean floor which is sliding underneath convergence with North America. That gives rise to the Cascade volcanoes, Mount St. Helens, Mount Hood, Lassen Peak, Crater Lake, etc. And that, as that subduction is giving rise to those volcanoes, that whole plate may be removed in the next 30 million years. So it is hard to sort of use the computer programs to try and like predict in the future what might happen. But that's the story. The last case, which is odd, has nothing to do with plate edges, but it does have to do with plate tectonics. When we presented the idea of plate tectonics, when Harry Hess sort of gathered our information together and came up with a coherent picture that we used to build on in 1960, one of the first challenges was the Hawaiian Islands, because they don't occur on a plate edge. And yet we get a line of islands that suggests that obviously magma has to be involved there somehow. If you take samples from the Hawaiian Islands, from Kauai to Hawaii, Kauai is the oldest, up to 5.6 million years old. Hawaii is the youngest, where we just had eruptions 2 years ago. So they decrease in age in one direction, and we think the plate is moving to the northwest. In the upper right-hand corner, we can see that we have these extant Hawaiian Islands, but still farther northwest, we have a whole bunch of Emperor seamounts. This gets into some of the islands like Midway, which is at the far left-hand edge right near a bend. And then we have other islands that go up here. at the far northwestern extent, this is 88 million years old. Midway is about 44 million. And of course, Hawaii effectively has an age of 0. What we think is going on, geologists who were critical of plate tectonics said, what do you think is occurring here? It's like some sort of hot spot. We went, damn, that's not a bad idea. And what we think might happen is, like a lava lamp, there are discharges of material from the base of the mantle, right at the boundary with the outer core. And we have these blobs of superheated material which rise through the mantle. And that's what this computer simulation is to show in the upper left. And as this giant blob hits the bottom of the lithosphere, like a blowtorch, it burns a hole and a massive volcano is formed on top. But while that blob is there, the plate just moves over top of it. And as the plate moves over top, a new volcano is formed. Plate continues to move, a new volcano is formed. And what do we get? A line of islands. Yellowstone, I mentioned in the video last time, formed because of a very strange phenomenon. We think this is what caused Yellowstone to form. It's just, instead of it being nice and happy like the Hawaiian Islands are shield volcanoes, it is horrendously explosive because it has to move through and melt much more viscous material. So what do we get? We get different types of volcanoes that don't occur on plate edges. Yellowstone is an example of one. Hawaii is another example of one, where we can get plates moving over top of these big sources of heat. If you notice in the lower right-hand corner, we have something called Loihi. It is a new, we think, a new complete volcanic structure being built southeast of the Big Island, and it will become the next island in the Hawaiian island chain.
No questions.
Max, yes, that is so. An atoll. So since we're talking about volcanic islands, an atoll is a good idea. Atolls are ring-shaped features made up of coral that appear in tropical oceans around the world. We see them most, some of the famous examples in the Pacific. We see Bikini Atoll and Eniwetak Atoll. We see these sort of ring-shaped features of coral. Coral is one of the most simplest creatures on Earth. It's basically a cup of tissue with some feeder tentacles on top, and it uses seawater and it secretes a shell around itself. And when we see coral, we tend to see a whole bunch of individual little cells that look really circular with these sort of like teeth-like structures in them. What we're seeing is the coral skeleton. The actual little tissue bag is gone, and what we're seeing left behind is the coral skeleton. Well, when a coral polyp, which is the little tissue bag with feeder tentacles, grows, it secretes a shell, it divides, and another polyp comes out, and then they grow. And so what we see are a whole bunch of these little coral polyps forming a collective head. Well, if they're some of the simplest creatures on Earth, why do they make ring-shaped structures in the oceans? And when I show that, I'm going to pull up an image here, and hopefully I'll be able to do this. Hopefully you'll be able to see this on the screen. If it doesn't pull up, I will change my image.
What'd you do?
Hold on. Okay.
Hold on, I do see
the image will flash here in a moment, because this is fundamentally related to volcanoes, and this is awesome. So, and Max, you can correct me on this. This is Eniwetak Atoll that you'll see pop up here in just a second. I hope.
Video?
You'll see my head first, and then it'll pop up.
Yep, I see your face. Let's see.
So, one of the simplest creatures on Earth, but they can make a structure which in this case is 15 miles across. When geologists saw these, they went, well, how? How could this happen? Charles Darwin, when he was doing his famous travels on the Beagle, encountered these coral atolls, and he said, I have an idea. Since they're some of the simplest creatures on Earth, it makes sense this way. This represents a volcano. The coral attached to the volcano grew around it in a ring shape because the volcano was, in this case, roughly ovular, right? And as the coral would grow around it, eventually the volcano would stop erupting. And once it stopped erupting, if it didn't continue to build itself up, then decay would break the volcano down. It would eventually disappear below the surface of the water. And then what we'd be left with is coral. Why? Because coral needs to be in sunlight. So the coral will keep growing up even as the volcano sinks. And eventually the volcano sinks so far, we don't see it anymore. And the coral grows in a ring structure. So when he presented that, people went, sure, not a problem, absolutely. But around 1920, Alexander Agassiz, who was a famous geologist, said, nonsense, that's just too simple. The coral has to grow up from the ocean floor. So the British Royal Survey sent a drilling vessel to, I believe they sent it first to Eniwetok. And when they drilled down about 1,300 feet, and all they got was coral. Well, that doesn't mean that Darwin was wrong, and it doesn't mean that Agassiz was right, because 1,300 feet might not be sufficient. So eventually, 1948, they went back to another atoll, and they drilled down 4,700-ish feet, and they hit volcanic material. So it turns out that Darwin was right, that what we have is a volcano that as it grew, coral just grew around it and kept growing upward. The volcano shut off, and as it shut off, the coral continued to grow and grow and grow. We don't see volcano anymore. What does that have to do with our lesson on plate tectonics? Well, if we have a plate moving over a hotspot and creating a volcano on the top, and coral grows on that volcano, eventually that volcano plus coral is shifted away from the hotspot. And then the volcano shuts off. And why does it shut off? Because eventually it's so irregular to have to put up magma erupting out of that particular volcano. So eventually it just goes, you know what, it's just easier for me to burn a new hole. So the plate with volcano and coral in tow just sort of moves up, new one is created. That coral continues to grow, volcano dies, disappears by erosion. Interestingly, this particular, the reason why I like drawing people's attention to this one, you'll see here in a moment, zoomed in, you'll see two circles. You can see them on this image, but you'll see here in a moment, two circles in the upper left-hand corner of this atoll. There are only certain portions of the coral which are actually visible above the surface. The rest of it is just below the surface. But people live on this this atoll. And Max has said there,
yeah, that their families, let's see, families were from the atoll before they moved everyone off because it was contaminated.
It was contaminated. These two circles in the upper left-hand corner are nuclear bomb tests. When we did the nuclear bomb tests, these holes were generated in the coral. And what we did is we moved the Marshall Islanders off, and then we moved them back on in some of the islands. And there were stories that some of the kids experienced snow for the first time. That was essentially precipitated coral falling out of the atmosphere. And they got burns on their bodies, etc. But that's what you're actually seeing there. Those are nuclear bomb tests in the coral at the edge of the atoll. One funny story. I'm going to give one funny story, and we're going to go back to the demonstration here in just a moment, and we can see something about it. Let's see. Stop share. And then I'll open it up for questions. In the 1920s, because of a growing population in the southwestern United States, because of the realization that so many people were moving to the region, because the growing season was great, even though they didn't have abundant water, the government built the Hoover Dam in the Colorado, across the Colorado River. When they built the Hoover Dam, it was a marvel of modern engineering. And it still is a marvel of modern engineering. And the Hoover Dam sits across the Colorado River. Behind it, we have this massive lake we call Lake Mead. We have these massive intakes for hydroelectric power, et cetera. When we built that dam, we broadcast to the world how tall it was. Because it was one of those things like, 40 years ahead of its time. We're like, this will be a question on Jeopardy. Everybody wanted to know how tall it was. Well, to make sure there were no problems, we would periodically go back out and resurvey the height of the dam in the center. Well, a couple years go by after Lake Mead starts to pond behind it, and the dam has begun to sink. Now, it never sank more than a couple inches, but we were so precise in our measurements. We're like, why is it sinking? Why is it sinking? And that terrified us because if it starts to sink, that could be a runaway scenario and the entire dam gone. Well, eventually the sinking stopped. And geologists went, why did the sinking stop? Then they mapped out the area of sinking, and it was directly related to the dam and the water ponded behind it. And we went, what the? And then somebody smacked their head and said, we didn't think it was possible. The sinking was caused by the sheer weight of water in an area that it had not previously been. And what it was doing was just deforming the asthenosphere below. So even though the asthenosphere was 40 plus miles deep under the Hoover Dam, the sheer volume of water and the dam itself, confined to such a small area, actually compressed the asthenosphere like a disc between vertebrae in your back. And once enough water ponded in that area, it balanced out and it stopped. And we went, huh, we never thought that if we built something, we could actually influence the asthenosphere. And that's not something when you can get out, you're trying to build a dentist office or something, nobody goes, do you have asthenosphere insurance? That doesn't happen. But it's something that we didn't think about. And at massive scale projects, it could actually cause discernible effects, not problems, because we haven't had a problem with that, discernible effects. Now, interestingly, Northeast, last ice age, ice was up to a mile thick in down to southern Illinois, parts of Ohio, Pennsylvania, New York State, etc. Every once in a while, we will get a minor earthquake in New York State. When we were there, my wife and I were there. Every once in a while, we'll get a minor earthquake there. And geologists say that many of those are due to unloading. The ice had packed down the region in the past, which would have influenced the asthenosphere. And now that the ice is gone, it's like the house popping back up. Rather than settling, it's sort of lifting, and it'll create generally minor but detectable earthquakes in the Northeast. And that's amazing. So that's plate tectonics in a nutshell. Our general idea, we had our evidence. We said, okay, it's not that the tides are moving it. There has to be something else. Then we started building the case. Something has to go on. We found the evidence in the ocean floor. We found the evidence in the earthquakes. We studied the layering of the earth. And I could go in, we could talk about magnetism, which is awesome. Excuse me. We could talk about a whole host of other pieces of evidence for this. These are the dominant ones. And so what do we have? We have the Earth's surface, the lithosphere, broken up into a bunch of chunks. And those chunks either slide apart, pull apart, they collide together, or they slide past one another. California will not fall off into the ocean, so do not buy your desert lakefront property. Are there any questions? Yes, Max. Yes, Megatron is the reason why the Hoover Dam is still sinking.
Proof that Megatron has a fat ass.
Wow. Yes, that's probably true.
Oh, Bayverse Megatron.
Ow.
What?
I had not heard that particular story, Max. The Marshall Islanders, some people thought the stuff falling from the sky was manna and they ate it.
Ooh.
Any questions?
Big
Any
crunchy.
questions?
Give it a minute. Jeez. Remember, there's a 10-second delay. So. Still no questions.
I may put some links in the description for more clarity on some things, sort of animatics, etc. Because I think that might actually be useful, especially for somebody who has not watched this in real time and wants to go back and go, hey, I have a question.
Don't chew that, please. Don't chew that.
Yes, that is exactly right, Max. It is amazing to think that we could though actually affect that. And this goes in, I think it's the Three Gorges Dam in China, where they've actually seen the ponded water has actually led to earthquakes because the sheer mass of the dam has caused slippage at the surface. My wife is looking that up.
Some of them it suggested that it may actually the water may have reactivated existing fault lines
On the Three Gorges Dam.
Yes, so unidentified faults that potentially were put under additional stress due to the weight of the water.
So it could very well be. If I can find more, I'll put it in the comments. The Three Gorges Dam, one of the largest dams in the entire world, one of the largest dam systems in the entire world in China, may have reactivated faults that either we didn't know about or we thought hadn't moved in ages because the sheer amount of water behind the dam, or what?
Now, continue talking. There may be so the Chinese ex-Chinese experts suggest there may not be any connection. So
that's a possibility, but we'll look into that, and I'll try and put that in the comments. Thank you for joining us again. Blackland Geology and Reptiles. I'm Brett Burkett. My wife is sitting down here. If I can, we'll get a better camera set up here. Right now, I have been sweating because the camera is just, or the light has just been broadcasting onto my head and creating a whole bunch of reflections because I don't have much hair. Blackland Geology and Reptiles. If there's anything that you're interested in, put it in the comments. Next Friday, we'll do another one.
Next Friday is probably going to be an art stream.
My wife is going to do an art stream next Friday. Mm-hmm. And if anybody is interested in midweek science, sort of something shorter, and it probably, I promise it will be shorter than Mount St. Helens, that was an hour, put it in the comments and I will do that if I can. Maybe I'll just talk about magnetism because like ICP says, how do they work? Have a good night and thank you for joining us.
Really?